Alright, so this is our Honors Chemistry Section 8.2 lesson video part 4, the final one. So see, I tried to warn you in Section 8.1, these sections are super long. 8.3 and 8.4 are going to be just like this. Alright, so the next thing we're going to talk about is the strength of covalent bonds, and eventually we're going to get into bond enthalpies. So the stability of a molecule is related to the strength of the covalent bonds it contains. The strength of a covalent bond between two atoms is determined by the energy required to break that bond. So in order to break a bond, kind of like breaking a pencil, it requires energy. So the more energy requires, the stronger we say the bond is. So the bond enthalpy is the enthalpy change, which is represented by delta H. So delta means change in, like think about when you do slope in math, how you have change in y over change in x. And so delta H is change in enthalpy. Enthalpy is represented by H. So for the breaking of a particular bond in 1 mole of a gaseous substance. So we use the designation D and then the bond type to represent the bond enthalpy. So it might say D in the parentheses C-H to represent a carbon-hydrogen bond. When molecules contain multiple identical bonds, we use the average bond enthalpy. So there are bond enthalpy charts that you can look up, or if you're in my class, you have one in your packet. And so all of these numbers are on that bond enthalpy chart. So all the numbers you'll see me use in the next couple of sample problems, that's where I'm pulling them from. So the bond enthalpy is always a positive quantity because energy is always required to break chemical bonds. The greater the bond enthalpy, the stronger the bond. And then a molecule with very strong chemical bonds generally has a less tendency to go through a chemical change than one with weaker bonds. So the stronger the bonds, the less likely it is to react with something else. So how do we calculate this? Well, when you calculate the delta H, or the change in enthalpy of a reaction using bond enthalpies, you use the following equation. So of course this just means summation. So our change in enthalpy for the reaction is the sum of the bonds broken minus the sum of the bonds formed. So we would just need to look at the reaction. The reactant sides are the ones we're going to break. The product sides are the ones we're going to form. So we're going to do bonds broken on this side minus bonds formed on this side. Now sometimes you might have to draw the Lewis-Dot structures to tell what bonds we're actually looking at here. So let's look at the first one together. So it says, using table 8.4, which is in your packet, estimate delta H for the following reaction. So remember, it's bonds broken, so delta H is your bonds broken minus bonds formed. I'm not going to write the whole summation and everything like that. Alright, so let's look at what we're breaking here. Alright, so I can see that I'm breaking a CH bond, but I'm breaking more than one. So if you look, I'm breaking 1, 2, 3, 4, 5, 6. So I'm actually breaking 6 CH bonds. Okay, so I'm going to bracket this. So I have 6 times whatever a CH bond is, plus I'm also going to break this CC bond. I'm only going to break one of those. So plus a CC bond. Plus, now whenever you have a coefficient, you have to multiply your bond by that. So one thing you need to make sure you know is O2 is a double bond. So again, if you didn't already know that, you would need to draw that one. But that might be something you just want to memorize. O2 is an oxygen double bond. Okay, so I'm breaking 7 halves of that. Notice it has a 7 halves. So I'll do 7 halves times an oxygen double bond. And then that takes care of my reactant side, my bonds broken. Then I do minus my bonds formed. So I'll look over here. I have 2 C double bond O's. So see, a C double bond O, C double bond O. But I have a 2 in front. So I really have 4 C double bond O's. Plus, I also have 2 OH bonds, single bonds. OH single bonds, but times 3, so I have 6 OH single bonds. I guess I don't really need double parentheses here. I'll take those off. I think that might be, same thing over here. I feel like that might be getting confusing if I do a double parenthesis. Alright, so once you have this set up, that's when you look at that chart. the table 8.4 in our book. If you're watching this online and you're in someone else's class, I don't know where yours is necessarily. All right, so I went ahead and pre-wrote mine down. So here I would have 6 times a CH bond on our chart is 413 kilojoules, plus a CC bond on our chart is 348 kilojoules, plus 7 halves, and oxygen-oxygen double bond was 495 kilojoules. So those are my bonds broken, and then I do my bonds formed. So a C double bond O was 799 kilojoules, and 6 times an OH bond is 463 kilojoules. See, the important thing is, y'all, make sure you put this in the calculator correctly. Use the correct parentheses and whatever you need. Make sure you're subtracting this entire portion and not just part of it. But what you should get when you actually put all this in is that your bond enthalpy change in this reaction is negative 1,416 kilojoules. Now, I know some of you may be thinking, wait a minute, I thought you said all bond enthalpies are positive. That's the energy required to break one bond is positive. And when you're talking about a reaction, you can have an overall negative change in enthalpy. It just actually took energy to break all the bonds, but energy is released when bonds are formed. So what that means is more energy was released from forming these bonds than was needed to break the original bonds. Okay, so energy is always required to break a bond, and energy is released when bonds are formed. That's why we subtract it, because that makes this value negative, because that energy is released because it's a favorable process for a bond to form. Because remember, bonds form to make atoms more stable. So that's a favorable process. Alright, so maybe pause the video and you try the next one. I'll give you a minute to do that, and I'll assume that you've done that now. Alright, so remember, our delta H for the reaction are our bonds broken minus bonds formed. So I'm going to start with my bonds broken. So I can see over here I have an NH bond, but I actually have 1, 2, 3, 4 NH bonds. So I'm going to do 4 times an NH bond. Then I also have an NN single bond. So I'm going to do an NN single bond, and that's everything I'm breaking. Then I'm going to subtract my bonds that are formed. So here I have an NN triple bond. And here I have an HH bond, but I have 2 of them, because see how there's the 2 right there? So 2 HH bonds. All right, so next I'm going to look at my table, which of course I already have mine pre-written down here. So I have 4, and an NH bond on our table is 391 kilojoules, plus an NN single bond is 163 kilojoules, minus my bonds formed. So an NN triple bond is 941 kilojoules. That's a very strong bond. Plus 2 times an HH single bond is 436 kilojoules. So once you do all the math for that, you should have gotten about negative 86 kilojoules. All right, so the hardest part about these is, like I said, if they don't give you the bonding, you may need to draw Lewis-Dot structures to figure out the bonding. And we'll do one of those at the end of this lesson video so you can see what that would be like. All right, so hopefully, though, you didn't find that process too difficult. Bonds broken minus bonds formed. And just pull the numbers from the chart. So as the number of bonds between the carbon atoms, or any atoms, increases, the bond enthalpy increases and the bond length decreases. That is, that the atoms are held more closely and tightly together. So in general, as the number of bonds between 2 atoms increases, the bond grows shorter and stronger. So, for example, if we look at our carbon ones right here, we have C single bond, double bond, triple bond. So if you look, the bond length is decreasing. So CC single bond is 0.154, a double bond is 0.134, and a triple bond is 0.120. So our bond length is decreasing as we get more bonds. However, if you look at the enthalpy, the CC single bond is 331, a double bond is 590, and a triple bond is 812. So the enthalpy is increasing. So like I said, as you get more bonds, the bond length gets shorter because the atoms are held closer together, but the bond enthalpy increases because it takes more energy to break it. So think about this, if you're holding one pencil versus 3 and you have to break them, the 3 is going to take more energy. All right, oh my gosh, we have gotten to the end. All right, so we are at the sample integrated exercise, and this first part I looked at and I remembered you can't actually do this part yet because we don't learn how to do this until Unit 4. So I'm going to have to give you the formula. So the formula is COCl2. But after Unit 4, we'll know how to calculate it. So phosgene has the following elemental composition, and like I said, I'm just going to go ahead and tell you it's COCl2. So draw 3 Lewis structures for the molecule that satisfy the octet rule for each atom. Okay, so we got to draw our Lewis dot structure. So first step is I'm going to add my valence. So C is in group 14, so it has 4. O is in group 16, so it has 6. Cl is in group 17, so it has 7 times 2. So we have 14 plus 10, which is 24 valence electrons to work with. Step 2 is single bond everybody. So I'll go ahead and tell you this one. I would tell you how to set up. Your O and your 2 Cl's are going to bond to carbon. So carbon's going to be in the middle. So I'm just going to do it like this. I'm going to do my O going up and my Cl's going across. All right. So next step is octet and duet rule. Well, all of these follow the octet rule. So O has 2, so it needs 6 more. Cl has 2, so it needs 6 more. Cl has 2, so it needs 6 more. And C has 2, 4, 6, so it needs 2 more. So we got our structure all taken care of. So next we need to total our valence electrons. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I have 26 electrons. I am only allowed 24. So I have 2 extra electrons. So remember, for every 2 extra, I need 1 bond. Whoop, I wrote 1 bod. 1 bond. So the important thing is, of course, where do we put it? That's why it says draw 3 structures. We have resonance here. Okay, so I could put it to the oxygen. So don't forget, once you add an extra bond, you need to readjust for the octet. If I add it to oxygen, oxygen now has 2, 4, 6, 8, 10, so I will remove 2. Carbon has 2, 4, 6, 8, 10, so I will remove 2. So that's one option. All right, I also could have put the double bond to one of the Cl's instead. So let me add all my electrons back. So this is what we would have started with. This is before I readjusted, in case you're getting a little lost. So I counted, realized, hey, I have 2 extra, I need a bond. I chose to put it here, so I'm going to readjust. So this Cl has 2, 4, 6, 8, 10, so I would remove 2. Carbon has 2, 4, 6, 8, 10, so I would remove 2. Or, of course, I could put it to the other Cl. So in that case, it would look a little bit like this. So once I choose to put it here, I would readjust 2, 4, 6, 8, 10, so readjust to 8. 2, 4, 6, 8, 10, so readjust to 8. So these would be my 3 resonance structures. So for one, I could have a double bond to oxygen, and for the other 2, I could have double bonds to chlorine. All right, I'm going to leave this up because I know the next question deals with these. All right, but I'm going to go ahead and click so that we can see what the next question is. So it says, using formal charges, determine which Lewis structure is the most important one. Okay, so here we have Cl. Cl starts out with 7 valence electrons because, of course, it's in group 17. And remember, I'm going to split the bond. So I gave it 1, 2, 3, 4, 5, 6, 7. So 7 minus 7 is 0. So that Cl has a 0 charge, or formal charge. All right, next I'm going to do C. So C has 4 from the periodic table, 4 valence. I'm going to split my bonds. So I gave it 1, 2, 3, 4. So 4 minus 4 is 0. Oxygen starts with 6. It's in group 16. I split my bond. I gave it 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. And then last, chlorine has 7. I gave it 1, 2, 3, 4, 5, 6, 7 because I split my bond, so it is 0. So hopefully you can obviously already tell that because all the formal charges are 0, this is our favored one. But just in case you need more practice figuring out formal charge, I'll show you what it is on these. And plus, you do always have to check and make sure they aren't all favored. Some resonance structures are favored just as much as others. It doesn't always help us pick a favored one. So let's make sure the rest of them don't all have zeros. All right, so I'm going to start with this Cl. I'm going to split my bond. So Cl starts with 7. I gave it 1, 2, 3, 4, 5, 6. So 7 minus 6 is a positive 1. Oxygen starts with 6 on the periodic table. I'm going to split my bond. I gave it 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is negative 1. Carbon starts with 4. I'm going to split my bond. I gave it 1, 2, 3, 4. So 4 minus 4 is 0. And then chlorine starts with 7. I gave it 1, 2, 3, 4, 5, 6, 7 because I split my bond and so I got 0. So because this one has a negative 1 and positive 1 instead of all zeros, that would not be a favored one. So then let's look at our last one. So here, chlorine starts with 7, and I'm going to split my bond. So I gave it 1, 2, 3, 4, 5, 6, 7. So 7 minus 7 is 0. Oxygen starts with 6 valence electrons. Split my bond. I gave it 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is a negative 1. Carbon, split my bond, starts with 4, but I gave it 1, 2, 3, 4. So 4 minus 4 is 0. And then chlorine starts with 7 off the periodic table. I gave it 1, 2, 3, 4, 5, 6 because I split my bond, which gave me a positive 1. So because the first structure with the double bond to the oxygen has all 0 formal charges, that would be the favored resonance structure. And I think I need that resonance structure for the next question, so I'm not going to refigure it out. I'll just draw it the way it was. So it says, using average bond enthalpies, estimate delta H for the formation of gaseous phosphine from carbon monoxide and Cl2. Okay, so we're forming the phosgene. Okay, so I'm just going to put what I had over there. I'm not going to, show you how to draw it again. So that's what I had. So this is what we formed. It says from CO. So we need to draw the structure for CO. So first, I got to add my valence. So C has 4 because it's in group 14. O has 6 because it's in group 16 for a total of 10 valence electrons. All right, so I'm going to bond everybody. So C, O, and then I'm going to follow octet duet rule, which both of these follow octet. So C has 2, so I add 6 more. O has 2, so I add 6 more. And then I check my total. So I have 2, 4, 6, 8, 10, 12, 14. So I have 14 valence electrons. I'm only allowed to have 10. I have 4 extra electrons. So that means I need 2 bonds. So I'll put a triple bond instead, and then I need to readjust for the octet. So carbon has 2, 4, 6, 8, 10, 12. So I get rid of 4 electrons. Oxygen has 2, 4, 6, 8, 10, 12, so I get rid of 4 electrons. So let me just check my total again. I'm allowed 10. I have 2, 4, 6, 8, 10. So see, this is what I'm saying. If you didn't draw the Lewis-Dot structure, you might not realize that CO has a triple bond instead of a single bond or a double bond. All right, so then we're going to add Cl2. So let's do the Lewis-Dot structure for that. So Cl has 7 valence. We're going to add our valence first. Has 7 times 2, so that's 14 valence electrons to work with. Second step is I single bond everybody. Third step is octet duet rule. So they both follow octet, so 2 for chlorine, so I need 6 more. 2 for chlorine, so I need 6 more. Check my total. I'm allowed to have 14, 2, 4, 6, 8, 10, 12, 14. All right, so in other words, now I can see what bonds are broken and what bonds are formed. So that's what I mean by sometimes you have to draw the Lewis-Dot structures to be able to tell. Sometimes they give you the bonds. It just depends. All right, so remember our delta H is bonds broken minus bonds formed. All right, so let's write out what it would be first. And y'all, once you get good at these, you don't have to sit there and write everything out like I'm doing right now. Okay, so we're going to break this CO triple bond. We are going to break a Cl-Cl single bond. And then bonds formed. So I'm going to form two CCl bonds. So see, here's a CCl bond, here's a CCl bond. So we're going to form two of those. So I'll put it times 2. And then we're going to form a C double bond O. All right, once I know that, I can look at my chart and fill my numbers in. So a C triple bond O has a bond enthalpy of 1,072 kilojoules. A Cl-Cl single bond has an enthalpy of 242 kilojoules. Then we have two CCl bonds, which CCl has a 328 kilojoule bond enthalpy, and a CO double bond, which has a 799 kilojoule bond enthalpy. So once I solve for all that, I get negative 141 kilojoules. And so like I said, sometimes you just have to draw the Lewis dot structures to figure out the bonding. All right, so let's move on to our section assessment. So what electron configurations do atoms usually achieve by sharing electrons to form covalent bonds? Atoms in general bond to be like a noble gas. So they like to achieve noble gas configuration. So in other words, they want 8 valence electrons, or the ones that are near helium want 2 valence electrons. So they're trying to be like a noble gas. Number 2, when are two atoms likely to form a double bond? When a single bond, they're sharing 2 electrons. So they would form a double bond when they need to share 4 electrons, and then they would form a triple bond when they need to share 6 electrons. Okay, so it just depends on how many needed to be shared as to what type of bond is formed. So number 3, how is a coordinate covalent bond different from other covalent bonds? In a coordinate covalent bond, one atom donates both electrons to be shared in the bond. So like the bond is made of 2 electrons that are shared. So in coordinate covalent, one atom shares both the electrons. In normal covalent bonds, each atom donates 1 electron to be shared in the bond. So it's like you're going on a picnic. Okay, say 2 people are going on a picnic. A normal covalent bond, one person can be like, hey, I'm bringing sandwiches. One person can be like, hey, I'm bringing chips. And then they could share sandwiches and chips. So they each brought something and they each shared them. However, a coordinate covalent bond would be like, hey, we're going on a picnic. And one person say, hey, I'm bringing sandwiches. And then the other person could be like, oh, I don't have any money. I can't bring anything. So then the first person could say, oh, I'll bring the chips too. So that person could bring the sandwiches and the chips and still share with the other person even though they didn't bring anything to the picnic. So really, a coordinate covalent bond is just a super generous atom donating both electrons to the bond. So number 4, how is the strength of a covalent bond related to its bond dissociation energy? The stronger the bond, so stronger bonds have higher bond dissociation energy. Okay, BDE is just bond dissociation energy. So the stronger the bond, the more energy it takes to break it, which makes complete sense. Alright, so let's move on. Oh my gosh, we officially done with section 2. Oh gosh, there's still 2 more sections. Oh man, so many videos. Alright, what kinds of information does a structural formula reveal about a compound it represents? Okay, so y'all, let's first talk about what a structural formula is. So the chemical formula for water is like this. That's the chemical formula, H2O. The structural formula is like the Lewis dot structure. So what does the Lewis dot structure show us that the original formula doesn't? It shows us the bonding and arrangement of atoms. So I know I'm writing this down here, but it goes with number 5. it shows us the bonding slash arrangement of atoms. You could also say it shows the lone pairs, something like that. Like the original formula, it doesn't tell us that the two H's aren't going to be bonded together. We don't know that by looking at this. Here we can clearly see, oh, both H's are bonded to the oxygen. All right, and then number 6 says draw the electron dot structures for the following molecules. Okay, so we're going to follow our steps. So step 1 is add our valence. So we have H2S. So H has 1 valence electron because it's in group 1. I'm going to multiply that by 2 because there's 2 of them. S is in group 16, so it has 6. So I have 8 valence electrons to work with. Step 2, single bond, everybody. Since S is the single atom, I'm going to put it in the middle and bond my 2 H's to the S. Step 3 is octet and duet rule. So hydrogen follows the duet rule, so it already has 2, and this hydrogen already has 2. S follows the octet rule. Right now it has 2, 4, so it needs 4 more. Next step is check my total. I have 2, 4, 6, 8, and I'm allowed to have 8, so there's my structure. Okay, now even though we learned the harder ones, not all of them are harder ones where you have exceptions and charges and resonance structures. Some of them are just simple. All right, so next we have pH3. So first I'm going to add my valence. So P is in group 15, so it has 5 valence. H is in group 1, so it has 1 valence, but I'm going to multiply it by 3. So it also has 8 valence electrons. So next step, single bond, everybody. Well, since P is the single atom, P is going to go in the middle. Go bond all my H's. Next step is octet and duet. Well, hydrogen follows the duet rule, so there's 2, 2, 2. P follows the octet rule, so right now it has 2, 4, 6. So it needs 2 more to make 8. And the next step is check my total. I have 2, 4, 6, 8. I'm allowed to have 8, so there's my structure. So again, don't always assume, you're going to need multiple bonds and all that kind of stuff. Like some of them are just basic. All right, so next we have ClF. So Cl is in group 7 because we're going to start by adding our valence. So it's in group 17, so it has 7 valence electrons. F is also in group 17, so it has 7 valence electrons for a total of 14. So next step is I'm going to single bond them since we just have Cl and F. That's my only option. And by the way, that is Cl and F, not CIF. All right, so next step is octet duet rule. Both of those follow the octet rule. So right now Cl has 2, so I'm going to add 6 more. F has 2, so I'm going to add 6 more. So next step is, of course, check my total. So I'm allowed to have 14, 2, 4, 6, 8, 10, 12, 14, and so that is my structure. All right, oh my gosh, that was a lot of lesson videos. So hopefully Lewis dot structure isn't too tricky for you. I personally love Lewis dot structure. And so hopefully throughout this, what seems like an infinite amount of time making lesson videos, hopefully you've gotten at least a little bit of it. If you need more help, just let me know in class.